Alright, so we got workshop 9. This one was all on eigenvectors and eigenvalues, characteristic polynomials. Good times. So, 1. Find both the characteristic polynomial and its roots for each of the following. So, they give me this matrix. This is basically something you need to know, or just memorize this, but you get A and you subtract lambda times the identity matrix, and that's supposed to equal 0. The determinant has no area. It has something to do with lambda not changing during a linear transformation. I'm not quite sure exactly what it means, but I could compute them. So let's go ahead and do that. So I go ahead and compute that. I get this matrix. I take the determinant of that. That's going to be negative lambda times negative lambda minus 1 times 1. So that's going to give me my characteristic polynomial. That's what this guy is. And then I can just split this up, go ahead and solve for my roots. So I get lambda equals 1 and lambda equals minus 1. So that's all it wanted in that question. So B, I go ahead and I do the exact same thing. So this is really tedious. So basically I get down to this point here where I'm subtract 1 minus lambda and 4 minus lambda, or what's going to end up in your determinant here. And then you go ahead and multiply this out. You'll get this. And I didn't know how to factor it, so I went ahead and used, well, I got to this point here. I couldn't factor that. Went ahead and used the quadratic formula. I get these god-awful looking things. And this is, this is what's going to slow you down later, because we actually use all of these in the next section. So, yeah, this was a long one. C, we're going to go ahead and do that. Same thing. So 1 minus lambda, 1 minus lambda, that's going to go here. We get those two guys. We get our characteristic polynomial. I then resort to this guy to find the roots. Find out I've got imaginary roots. So I get 2 plus or minus square root of 16 times, well, 4i, right? I have the square root of minus 1. So I get lambda equals this guy or that guy. So find eigenvalues. Already done. So these are the eigenvalues that we're going to be using. The ones highlighted in green. Of the eigenvectors. So we want to find the eigenvectors. So we're going to go ahead and compute them all. So for the first one, we had lambda equals minus 1 and lambda equals 1. So this one's not too bad. You go ahead and augment. Well, basically, you're doing 0 minus lambda, right? So I'm going to get this matrix here. If you augment it with 0, you can then reduce it. You'll find that x2 gives you a parameter, and you can solve for x1 in terms of that parameter. So you get it in the form of this. So I don't know if that's good. He likes to call it V, but like, God, why don't they just use that? So I've been using this to denote the eigenvector in all of these cases here. Maybe I'll use V on the actual test, but it just makes, why don't they do that? It's probably a good reason. Anyway, maybe it's for the textbooks. So yeah, you're going to get minus t. So I'm just going to plug in t equals 1. Doesn't matter, you can scale that all you want. It's still pointing in the same direction. So that's that eigenvector. And we go ahead and do the same thing with 1, but this becomes minus 1 because it's 0 minus lambda, right? So that becomes this. In general, if you got a 2 by 2 like this, you're always going to get zeros on the bottom. That'll come into effect later. It's more obvious here because you can just go ahead and add the 2 rows and you'll get the same thing. Well, it looks like we got the same answers for x1 and x2 in terms of t, because x2 is a free variable. Anyway, so we get lambda, the eigenvector rather, is going to be 1, 1 at lambda equals 1. So Now we're going to do this one, which generated two different eigenvalues. You see these ones take a little longer. So we're going to use this one. The exact same process. It's a recipe. You go ahead and do this. You get these guys. And remember what I said about you just go ahead and put zeros down at the bottom. Just do it. Don't bother with the arithmetic. If you can just do it for the 2x2, just do it like that. You'll save yourself a boatload of time, which is something you're going to I know I'm going to run out of time on the final. So, yeah, so we keep going. We solve for this because x2 is equal to t. And we solve for x1 in terms of t. And then we go ahead and get this one. I'm going to use a t value of 3 plus the square root of 33 just to cancel that out to get something that looks a little bit cleaner. Anyway, so that's going to be our eigenvector for that one. Do the exact same thing for this. You can see there's a theme. So lots of arithmetic. Watch your minus signs. Keep going. Put zeros down here. I can't do that with the 3x3s, but these ones you certainly can. The 3x3s they gave us at least were a little more well behaved. So just pray you don't get something like that in a 3x3. Anyway, so we go ahead and we get that. Great. Now for the imaginary stuff. So we go ahead and pop this in. This is our matrix. We're going to get this out of it. Go ahead and put zeros at the bottom. X equals t. Solve for x1 in terms of t. That'll give us t over I, right? Remember, 1 over I is the same thing as negative I. Go ahead and plug that in. And you'll get this as your eigenvector for t equals 1. Same thing with this one. If you can hear weird sounds, that's my dog. She's snoring. She's cute. We just got her the other day. Let's see. She's having a dream or something. Anyway, she's also distracting. So anyway, you go ahead and keep going with this. Go ahead, same recipe. Zeros. x2 is free. Solve for x1 in terms of x2. So it's over negative I, which means it's it. So it's just the trick to these particular ones is just know this conversion, and then you're good. All right, 3. Now we're in a little more hairier stuff. It's not too bad though. Here's our matrix. This is the same thing we used up here. I wrote it out. A minus lambda I. Same process, right? So these aren't too bad to compute. All right, go ahead, plug that in, get your matrix. Now this one, because it's a 3x3 determinant, we can use the what is that? Laplace expansion, I think it's called. So just remember your sign conventions. So this one here, it's like you're doing a cross product here. Yeah, it's just like a cross product. Anyway, we'll go ahead. I'm denoting this as the determinant because I don't want to write that over and over again. So we get this. That's 0 times I didn't care because it was going to be 0. This one also happens to be 0 as well. So when we multiply this out, this is going to be this times the determinant of this guy, which gives us this. And that's pretty much solved for us. So we get our 3 eigenvalues there. So let's plug those guys in. So we're just going to do a minus lambda, lambda I rather. So we get this. That goes to this. I don't show my row reductions, but you're going to reduce this all. This should really be augmented with the well, like I show here, this really should be augmented with zeros, but I just wanted to get it over with. So we go ahead, we got x1, x2, x3. x3 we see is 0. x2 is a free variable, so we'll use t. 2x1 minus 2t. We solve for x1 in terms of t. It's in this form when lambda equals 1. keep going. Exact same thing. Now it's minus 1, so you're going to add it. And you reduce, blah, blah, blah. x1, x2, x3. Solve for those. And we find that we get this eigenvalue here. X1 is 0 in this case. Yeah. Oh, right, because there's... Yeah, this... I ran into this. I thought it was 0 at first, but no, it's... x3 is 0. x2 is actually just free. I mean, it doesn't show up, so, but it's a parameter, so don't fall into that trap. Because I did. But anyway, so you get x2 is t. Go ahead. You can do it. 2. Same thing. x3 is free. We go ahead. Everything's in terms of t. Boom. Done. Part B. This one was different, but same recipe. Go ahead. Augment it. Or sorry, subtract lambda I from it. This determinant, we're going to use the Laplace expansion yet again. We're going to find that this guy goes to 0 because it's 0 times this minus 0 and this. And so really we only have to worry about this, and these are already factored out for us, thank goodness. And there we go. Beautiful. We got 2. Oh, why did we get 2? Right, because look, you see this is a common factor. That's going to come in handy later for this last bit. But yeah, we only got 2 eigenvalues here. So let's plug them in. Get them here to this point. Reduce it down. Now we've got 2 free variables. We've got 2 parameters now. It might have something to do with this. I don't know. I have a feeling that's what it's about. But anyway. So we get our 2 parameters. Solve for x2. Because it's in terms of x3. So now you get x1 equals t. x2 is this guy. 1/2 q, and x3 is q. I just wanted to get rid of the fractions because who likes fractions? But keep in mind, this is the t one, and this is the q one. So it's actually, excuse me, an eigenspace. So this is like the basis for the eigenspace. So I guess it's like a plane or something. Yeah, a plane that doesn't get squished. Because we're dealing with R3, so I guess there's a plane that doesn't get squished in that direction when you apply the linear transformation of this to it. Anyway. Or rather, it might get squished, but it doesn't change where it's pointing, if that makes sense. Okay, so lambda equals 2, same deal. Reduce it down. We only had one parameter in this case. x2 was going to be 0 because it was by itself. x3 was t. Go ahead and solve for x1 in terms of this. We get this vector here. I'm going to multiply by some nice values just to get me something that I like. And that's what we're going to have. So that's workshop number 9. Long one.